Welcome back to Think Design Work Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And what I have for you today is a review and a commentary of a now architectural concept and an architectural trend that relates to using more functional programming in your code because it allows you to make certain decisions later. Functional programming allows you to separate more cleanly some of the concepts in your code compared to the usual way we do it with object-oriented programming. You can definitely do the same things with object-oriented programming, but with functional they are kind of built in. And because of this, it is a very interesting approach for architecture. And in order to do that, we'll first talk about, and we'll first do a commentary on the on an InfoQ article called Late Architecture with Functional Programming. And then we will discuss an interesting, already from my view, a classical concept, although it's not used as much as I'd like to, which is a functional core and imperative shell. All right, so let's get started. First of all, this is the InfoQ article, Late Architecture with Functional Programming. This is a mix of a conversation, an interview, and a summary of a talk given by Michael Sperber, I think. I hope I'm pronouncing this name right. And the article is written by Ben Linders, published on 27 April 2023, so not so long ago. And the conversation goes like this, and the article goes like this. Many approaches to software architecture assume that the architecture is planned at the beginning. Unfortunately, architecture planned in this way is hard to change later. Functional programming can help achieve loose coupling to the point that advanced planning can be kept to a minimum and architectural decisions can be changed later. Michael Sperber spoke about software architecture and functional programming at OOP 2023 Digital. Sperber gave the example of dividing up the system's code among its building blocks. This is particularly important kind of architectural decisions to work on different building blocks separately, possibly with different teams. One way to do this is to use domain-driven design for the coarse-grained building blocks, bounded context. DDD says you should identify bounded context via context mapping at the beginning. However, if you get the boundaries between the contexts wrong, you will lose a lot of benefits. And you will get them wrong, at least slightly, and then it's hard to move them later. So I find this is true in practice. It's not true in the intent of the practice of bounded context. And actually, we reviewed an article by Matthias Werner and Matthias Verais and Rebecca Wurzbrock on how domain-driven design and this bounded context and the terms that you use there interact with the real world and how you need to take into account the feedback and integrate it into your bounded context. You should expect to get the bounded context wrong. And well, you lose a lot of benefits. This is a statement that if you get the context wrong, you lose a lot of benefits. I'm not sure this is completely true. It depends on how wrong you get them. And how wrong you get them depends a lot on the people you have access to, the domain experts you have access to, and how much you are listening. So indeed, if you approach architecture from a strictly technical perspective, and you start saying we need module A and module B, or however you discuss microservice A and B, that doesn't usually work that well. But if you sit down with domain experts, ask them questions, listen to what they have to say, it's unlikely that you'll get the contexts very wrong. They will not be perfect because you need to translate from their view to the technical view, and then there's an interaction, there's a feedback loop between the technical view and the real world that happens and that you need to take into account. So yes, you'll get them slightly wrong. Getting the context very wrong, it's hard for me to believe that this happens if you approach software architecture, let's say, with a humanistic perspective and not strictly from a technical perspective. Then yes, but then you'll get, or any architecture you'll get wrong. So it doesn't apply only to domain-driven design. If you approach software architecture strictly from a technical perspective, then yes, something will not work right. Oh, except for very specific cases, like if you are doing algorithms or, you know, Google search or something like that. Although even in that situation, you have specific queries that people need. So it's always a feedback loop, more or less. Okay. So already a few interesting statements. The second statement that I find interesting is that functional programming can help achieve loose coupling to the point that advanced planning can be kept to a minimum and architectural decisions can be changed later. I find this true, and for a few reasons that I guess we'll first go through the article and see how much they are developing these concepts. But it's true that functional programming is a very good way of achieving loose coupling. It's not the only way you can achieve loose coupling using object-oriented approach as well. But I think you need to be more careful. And with functional programming, well, for me it's difficult to imagine how you could not have loose coupling with functional programming. But from my experience, this is often the case that I have a blind spot, that I have never actually seen code written with functional programming that is tightly coupled. And I'm pretty sure that if you see a lot of code written using functional programming, you will end up seeing some tightly coupled code as well. But my feeling is that it's easier to achieve loose coupling with functional programming than it is with object-oriented, at least in the naive approach, let's say, more or less. Minimal effort approach, let's not say naive, but the minimal effort approach. All right. According to Sperber, functional programming enables late architecture and reduces coupling compared to OP. In order to defer architecture decisions, we must always decouple, Sperber argued. Yes, this is correct. More than that, you should define modules. That is one of the most important part. Components in functional programming are essentially just data types and functions, and these functions work without mutable state, he said. This makes dependencies explicit and coupling significantly looser than with typical OO components. This in turn enables us to build functionality that is independent of the macro architecture, Sperber said. Right, so this is correct, and when I wrote the book on functional programming in C++, I talked a lot in the book about decoupling, about how you can achieve decoupling with functional programming, how easy it is, and how granular it is. The fact that you can have functions that are pure functions, and lambdas and things like that. These are the main building blocks, and then you get design patterns like monads and other types of design patterns with functional programming that enable a lot of decoupling. Now, there is a downside here, particularly in programming language, in functional languages that are very strongly typed, like Haskell, and not only. Well, Haskell would be strongly typed. There's another one that I don't remember the name always, and is based on Haskell, if I remember correctly, and it's very strongly typed, meaning that you actually cannot write, so at compile time you cannot represent invalid values. That would be very strong type for me. Strongly typed is Haskell. Problem is with these languages, and particularly with the data types and functions that you create, problem is that you need to use a lot of abstractions, and it's okay as long as you are the one using those abstractions. The problem is that in time you either forget the abstractions and you don't remember exactly how they fit together, or for other people it's difficult to understand those abstractions. So this would be my critique on functional design in general. And actually what I would prefer is functional programming that is less strongly typed, and where the compiler does more of the work of figuring out what you want to say rather than what you are writing, if it makes sense. So, yeah, but as you may well know, I'm a strong supporter of doing less of the compiler work and having more smarter compiler. That's my general approach. So you can definitely use functional programming to achieve lower coupling. Issue is you generally end up with abstractions that are difficult to understand, and you need to pay a lot of attention there. But in terms of architecture, yeah, I think it makes a lot of sense. Sperber made clear that functional programming isn't just like OP only with mutable state. It comes with its own methods and culture, from domain modeling, abstraction, and software construction. Yeah, that's correct. You still get some benefits from using pure functions, a lot of benefits actually, but so pure functions would be immutable and context-free, but you can get some of the benefits just by adopting immutability in your whole project. To get all of them, you need to dive deeper and use a proper functional language, as Sperber explained. Functional architecture makes extensive use of advanced abstraction to implement reusable components, and more importantly, supple domain models that anticipate the future. In exploring and developing these domain models, functional programmers frequently make use of the rich vocabulary provided by mathematics. The resulting abstractions are fundamentally enabled by the advanced abstraction facilities offered by functional languages. And this is the crux of it. Because, okay, I loved and I love parts of mathematics. I still believe that a lot of that using these mathematical terms and structures in programming is not the best way. We should look at programming more like something between, and there were actually some studies on brains of people doing programming and many other things. And it turns out that programming is something that's between and requires both your mathematical brain centers and your language brain centers. So when we are using abstractions that are provided by mathematics, rich vocabulary provided by mathematics, those are not as easy to understand for most people. You might say that it's a training problem, that if we were trained into using those concepts, then probably we would do better. I'm not sure that is correct. I only have my own gut to base this on, but my feeling is that some programmers are more on the mathematical side, but they are a minority. And what we actually need is a rich vocabulary that is not provided by the mathematics, but that is provided by the domain. And this seems to be much easier to digest for programmers. Fundamentally, the way we should see software architecture, or part of software architecture, domain-driven design in particular, is to figure out a jargon that makes sense for the specific subdomain we are working on and within the technical context. And this is actually the job of architecture and design in this area. And we should learn not only from mathematics in this area, but also from linguists and the way jargons are created or they happen. But on the other hand, it's correct that these abstractions, reusable components, domain models, supple domain models that anticipate the future, yeah, I can definitely see how this can work for with functional programming. InfoQ interviewed Michael Sperber about how our current toolbox of architectural techniques predisposes us to bad decisions that are hard to undo later and what to do about this problem. What are the challenges of defining the macro architecture at the start of the project? A popular definition of software architecture is that it's the decisions that are hard to change later. Doing this at the beginning means doing this when you have the least information. Consequently, there's a good chance the decisions are wrong. I would argue that the decisions will always be slightly wrong. You'll always have not the least information, but less information than what you actually need. You just need to be able to adjust. And I think part of it is what we are discussing here as well, because supple and changeable, supple domain models that anticipate the future, from my point of view, what this means is that they can adapt to what we learn later. So, yeah. What makes it so hard to move boundaries between contexts? It seems in the architecture community we have forgotten how to achieve modularity within a bounded context or a monolith, which is why there's this new term modulith, implying that a regular monolith is non-modular by default and that its internals are tightly coupled. Well, because it usually is. Because the most common design patterns is a big ball of mud. There's actually a paper on this. So, yeah. And I don't think we have forgotten how to achieve modularity. I think the issue is we never actually achieved modularity, at least not to the level that we need today. So you are saying we don't know how to achieve loose coupling within a monolith. Yes, this is because the foundation of our architecture is programming with mutable state that is changing your objects in place. These state changes make for invisible dependencies that are hard to see and that tangle up your building blocks. This does not just affect the functional aspects of a project, but also other quality goals. That is true to some extent. The foundation of all architecture is programming with mutable state. This is something I do not fully agree. It is the most common approach to object-oriented, but the mutable state is actually not a core part of object-oriented. You can actually have object-oriented with immutable state. Or perhaps it was easier to program with mutable state. The key thing with objects is not as much, well, it is the encapsulation, but the important thing was messaging. And the hope was that messaging would achieve also loose coupling. But it was something that you need to take into account. And many of the design patterns, if you read them really carefully, they solve these problems in really good ways. Yeah, so, but I agree with him that the most common approach is, program with mutable state in object-oriented programs. Can you give an example? Let's say you choose parallelism as a tactic to achieve high performance. You need to choose aggregate routes and protect access to those routes with mutual exclusion. This is tedious work, error-prone, hard to make fast, and increases coupling dramatically. I feel that this is a very specific case. Parallelism as a tactic to achieve high performance. We've gone in various cycles here, and of course this is where functional programming shines. You can switch to parallel processing quite easily when you have immutability. But I find it a bit unfair to talk about the one specific situation where functional programming is fundamentally better than object-oriented, instead of discussing, let's say, the more general situations. But yeah, in this case, absolutely. Parallelism, it's easier to do with functional. It's easier to do with immutable state. So even with object-oriented with immutable state. What's your advice to architects and developers if they want to improve the way that they take architectural decisions? Even if you can't use a functional language in your project, play with the basics of functional programming to get a feel for the differences and opportunities here. If you are new to functional programming, I recommend the How to Design Programs approach to get you started. Okay. And there are some other books, Domain Modeling Made Functional and Algebra-Driven Design. These are books. I have heard of the first one. I haven't read it yet, but I think both of them sound very interesting. So yeah. All right. And this reminded me of the other approach, functional core imperative shell, which refers, well, it's something that you can use for your monoliths, but not only. So basically what you have is a functional core where you keep the domain logic in the functional core, and use immutable values and pure functions. What you actually have here is a mix of... All right, so I've implemented this in a few different ways to simplify it. One of them is a very functional kind of core, the one where if you change something, you get a new version, get a new object fundamentally. So using immutable data types, which is a very strong approach. The other one is where you have a separation between objects that are data types that are immutable, like entities. Well, not entities. It would be plain old data types. And like only with getters and setters. Or getters or setters or whatever combination you need. And then you would have another layer which is just services that work on this, get a value, do some processing, return something else. So it's a kind of a transformation pattern. And it's not fully what this means, but it is a good approximation of the pattern. Particularly easy to implement in technologies like in Java, on the web, and similar technologies. So keep the domain logic in the functional core, use immutable values and pure functions. Keep the infrastructure code in the imperative shell and use mutable values and functions with side effects. Yeah. So here you would get things like input, get the input and write to a database, log, all kinds of outputs. And then the imperative shell can call the functional core, but not vice versa. So only the imperative shell can call the functional core, but not the other way around. And you've done a good job if you can take this functional core, extract it, put another imperative shell around it. So if you can extract this, let's say you're doing a web application, a web monolith, if you can extract this and put around it a command line interface, a desktop interface, and so on, then you've achieved the decoupling, because that's the big thing. Now, if you have bigger domains, the key is to split the domain into smaller domains and then go the domain-driven design approach. Perhaps use different databases like you should with microservices. So you have a separate databases, and each of these functional core will write in its own database, and the imperative shell will basically write events, read events, something like that. This pattern enables us to use functional programming, what it does the best, and to use imperative programming for all the messy, mutable, side effectful stuff that most applications also need to do. This is correct because it's very weird to use functional programming for input-output operations. It's possible, but you need to understand certain concepts that are more difficult to understand. And by the way, going back to the book that I wrote on functional programming in C++, one of the things that I really wanted to do there was to explain monads without starting by saying this is a monad. And it was a small challenge that I had for myself. It took me a few years to be able to do that, but I definitely managed to do it. So if you want to understand monads, that might be a good way to do it. Right. What makes this pattern super nice is that it provides a clear separation between the two programming styles so they can peacefully coexist in the same application. Functional core imperative shell pattern is similar to hexagonal architecture, ports and adapters, clean architecture, and similar styles that, to be simplified, are characterized by two key architectural attributes. Yeah, so indeed, hexagonal architecture would say that you kind of have a hexagon and the connection with the outside world. So you have something in the center, which is your domain, and the connection with the outside world comes at the edge. Ports and adapters, very similar, but you have additional patterns of ports and adapters. Ports are things you can connect to, let's say, input output like console, logs, database, and so on, and then you need adapters to adapt data from the domain to the outside or the other way around. Clean architecture is a bit more mixed. It just describes a few layers that are separate and that are decoupled and so on. For some reason, clean architecture seems to be quite popular. I am not fully convinced by all the explanations. I've read the book, I've gone through a number of things. I still prefer functional core imperative shell, or let's say ports and adapters, but usually, to me, this is the best pattern for, at least for monolithic applications that you want to be modular. There is a core within the core business logic and a shell that handles interactions with the outside world, such as persisting data in databases or providing UIs to interact with end users. The shell can call the core, but the core cannot call the shell, and the core is even unaware of the existence of the shell. Yeah. This is also known as the dependency rule. So you should actually be able, this is what I was talking about. You should be able to have the functional core in a library, extract the library, plug it into another type of interface. So instead of being web, you have a command line interface, should still work. And what's the nicest thing about this is that you can test it. Because if it's not dependent in any way on the imperative shell, you can extract the functional core, test it with unit tests in memory that are very fast, and then test the integrations between the imperative shell and the outside world, and test the integration between the functional core and the imperative shell. Well, the other way around, between the imperative shell and the functional core, and you get very fast testing. An additional attribute in the functional core imperative shell pattern is, unsurprisingly, that the core should be written in a functional style, meaning using immutable values and pure functions. The key objectives in the functional core imperative shell pattern is to separate functional code and imperative code and to minimize the imperative code. So when in doubt whether a piece of functionality belongs in the core or shell, then make it functional and put it in the core. Yeah. And there are some more recommendations for articles here. I'll leave the link in the description, and this article is written by Kenneth Lange. So there's another thing that's interesting here, which is you can actually refactor toward this. And this is something I realized while writing the book on functional programming in C++, that you can actually refactor towards this by going through pure functions. It's quite easy to refactor to pure functions because you can use the compiler to get there. And then you can very easily write tests for pure functions, and then you can recombine the pure functions into classes and other things like that. So this is a very powerful, and I feel that it is a very fast approach to refactoring legacy code. But I'm still looking, and I have a whole, set of patterns and transformations that you can use here. But I'm still looking for an opportunity to be able to use this approach and refactor existing code, or rescue legacy code, or even rewrite parts of the code using this approach. All right, so this is what I have for you today. Functional programming and architecture. Is this something that you find interesting? Is it something that do you understand what it means, right? What are pure functions? What is immutability? Perhaps you'd like to see some examples. Maybe it would be interesting to do a kind of a product development using this type of approach, but I don't know, maybe in a specific technology, so on. I'm looking for more ideas about series on development and architecting and so on. So yeah, what do you think about this? Let us know in the comments. I love replying to comments, and we've had quite a blast this week and last week with conversations about architecture. So I hope you found this interesting. Thank you kindly for the view, and until next time, remember to think, design, and work smart.